Hello friends, so welcome to the lecture on spectral decomposition. We will learn about Eigen decomposition of a square matrix, means what we mean by Eigen decomposition. We will learn what is the necessary condition for Eigen decomposition of a matrix, because we cannot make Eigen decomposition of every square matrix. We will also learn spectral decomposition in case of symmetric matrix. Some of the algorithm where we will use this spectral decomposition include principal component analysis, spectral clustering. Many statistical machine learning algorithms use the concept of Eigen decomposition, reinforcement learning and many more. In fact, in many image processing applications also we make use of Eigen decomposition. It is also very important concept in case of when you are developing some recommender system. Okay. So, with this motivation, let me start with the definition of Eigen decomposition. So, let A be a square matrix. And let us say size of A is n by n. V1, V2, Vn, these are vectors from a n dimensional vector space, and these be the n linearly independent eigenvectors of the matrix A. Then A can be factorized as A equals to n invertible matrix P, a diagonal matrix D and the inverse of P. So, A equals to P D P inverse. Such kind of decomposition of A is called Eigen decomposition. Now, what is the relevance of P and D with eigenvectors and eigenvalues of A? So, the ith column of P is the eigenvector Vi, and it is an eigenvector of A. So, like how we are forming our matrix P, the first column is the first eigenvector of A, second column of P is the second eigenvector of A, and so on. And how we are forming D? So, D is a diagonal matrix whose diagonal elements are the corresponding eigenvalue of A. It means d I equals to lambda I. If lambda 1, lambda 2 and lambda n, these are the eigenvalues of A. Now, there is an important note, and what is that note? Every square matrix does not possess eigen decomposition. Means you cannot make this kind of factorization like A equals to P D P inverse for every square matrix A. A matrix should have certain property, then only we can make this kind of decomposition. So, what is that property, or in other words what is the condition to have an eigen decomposition? So, before going to that condition, let me give you an example of a 3 by 3 matrix for which we do not have eigen decomposition. So, let me take A equals to 1 1 1 0 1 1 0 0 1. So, it is a 3 by 3 matrix, and then if you notice the it is an upper triangular matrix, and in case of an upper triangular matrix the diagonal elements are the eigenvalues. It means lambda equals to 1 1 1 are the eigenvalues. So, in other word I can write that the eigenvalue lambda equals to 1 is having algebraic multiplicity equals to 3. As you can recall, the algebraic multiplicity is the number of repetition of the eigenvalue. Now, let us check the eigenvector. Corresponding to lambda equals to 1. So, for calculating this eigenvector A minus lambda I times V equals to 0. Here lambda is 1. So, A minus I times V equals to 0. Now, let me write in matrix form. A minus I will become 0 1 1 0 0 1 0 0 0 into V 1 V 2 V 3 equals to 0 0 0. By solving this, you can have V 3 equals to 0 from the second equation, and then from the first equation, since V 3 is 0. So, I am having V 2 equals to 0. So, V 1 is arbitrary. So, I can have only one linearly independent eigenvector corresponding to lambda equals to 1. So, the geometrical multiplicity of lambda equals to 1 is 1. Now, if I take V 1 as 1, the eigenvector V is nothing just 1 0 0. In the previous slide, I have told you that the columns of P are coming from the eigenvectors of A. You are having only one eigenvector of A, Li eigenvector. So, you can make only one column. but the size of P is 3 by 3. So, hence for this matrix A we do not have Eigen decomposition. So, what is necessary to have Eigen decomposition? If it is n by n matrix, then we should have n linearly independent eigenvectors for that matrix. In case of each eigenvalue, the algebraic multiplicity must be equals to geometric multiplicity. So, now condition, let me write here. So, what I can say? We need algebraic multiplicity. So, I am writing M in short equals to geometric multiplicity for each eigenvalue of A. And if you sum all the algebraic multiplicity, means in case of every eigenvalue, then it will be equal to the size of the matrix. In other word, the matrix A should have n linearly independent eigenvectors. Or in other word, the eigenvectors of A forms a basis of n dimensional space, n dimensional vector space on which the matrix A is defined, means it is a linear transformation. So, this is the condition for Eigen decomposition. Now, let me come to spectral decomposition. And this I am explaining in case of symmetric matrices. We are having more generalized class like in case of normal matrix, but here in machine learning in most of the cases we use symmetric matrices. So, I am explaining this spectral decomposition in case of symmetric matrix. So, let A be a n by n symmetric matrix. Then the Eigen decomposition of A is guaranteed. Why I am saying? For every symmetric matrix you can perform the Eigen decomposition. For every symmetric matrix A you can perform the Eigen decomposition. Now, this means I can write A equals to P D P inverse. Now, consider lambda 1, lambda 2, lambda n are the eigenvalues of A and corresponding eigenvector we are having V1, V2, Vn are the eigenvectors of A. Then what? By this eigen decomposition I can write A equals to, I will write P, P is nothing, you take first eigenvector as the first column of P, V2 and so on up to n into the diagonal matrix D, where diagonal entries are eigenvalues of A, rest of the entries are 0 and then P inverse. So, this is your P inverse of this. Now, the eigenvectors of a symmetric matrix is not only Li, but orthogonal. You will be having orthogonal eigenvectors for a symmetric matrix. It means V1, V2, Vn forms an orthogonal set of eigenvectors, means V1 dot V2 is 0, V1 dot V3 is 0, or in general Vi dot Vj is 0 when I not equals to j. So, in that case the matrix P, which is having these orthogonal vectors as the column, is an orthogonal matrix, means every square matrix which is having orthogonal columns is orthogonal. It means P inverse equals to P transpose. It means the eigen decomposition of A can be written as P D P transpose. Now, I can write it A equals to V1, V2, Vn and then lambda 1 0 0 0 0 lambda 2 0. This is matrix D and then P transpose is first column will become first row V2 Vn. So, if I multiply it, I can write A equals to lambda 1 V1 V1 transpose plus lambda 2 V2 V2 transpose plus lambda n Vn Vn transpose, where if you see each term of this summation, what is this? It is a matrix of rank 1 n by n matrix. Similarly, again it is lambda 2 V2 V2 transpose is again rank 1 n by n matrix and so on. Okay. So, each of these term is rank 1 n by n matrix. So, I am having A equals to summation I equals to 1 to n lambda I Vi transpose. Such kind of decomposition of A into a sum of n rank 1 matrices is called spectral decomposition of A. Now, an special note or remark: each matrix Vi transpose for all I equals to 1 to n is the projection onto one dimensional subspace of Rn spanned by which one? Vi. Okay. So, means we are having each of this matrix is a projection transformation, okay, onto a subspace which is spanned by Vi. In other words, I can write, if I am writing this projection matrix as P. So, this linear map P operating on X equals to Vj Vj transpose X. So, this Vj Vj transpose which is equals to P is a projection map. And what kind of? It is so, it is an orthogonal projection onto the subspace spanned by the eigenvector Vj. So, let me close this lecture with an example. So, a very quick example let me take. So, consider a 2 by 2 matrix A which I am taking 2 1 1 2. So, I will show you the spectral decomposition of A. The eigenvalue you can calculate, you are familiar with eigenvalue. So, eigenvalues of A are 3 and 1. So, let us say 3 is lambda 1, 1 is lambda 2. The eigenvectors of A are means corresponding to lambda 1 that is 3 is V 1 equals to 1 1 and V 2 equals to minus 1 1. Now, what you do? You can verify this V 1 V 2, V 1 dot V 2 equals to 0, means they are orthogonal vectors, and it is obvious because they are eigenvectors of a symmetric matrix. Now, let us make them orthogonal. So, let me write V 1 equals to 1 by root 2 1 by root 2. So, each element of V 1 I have divided by the length of V 1 and V 2 equals to minus 1 by root 2 and 1 by root 2. It means I can write my P and D. So, P equals to, you write V 1 as a column. So, 1 by root 2, 1 by root 2 minus 1 by root 2, 1 by root 2, and you can have D equals to lambda 1 3, lambda 2 1 0 0, and then this eigen decomposition or spectral decomposition of A is A P D P transpose. It means it is 1 by root 2, 1 by root 2 minus 1 by root 2, 1 by root 2, 3 0 0 1 into not yeah 1 by root 2 the transpose of P okay. Now, The spectral decomposition of A can be written as lambda 1 V1 transpose plus lambda 2 V2 transpose. So, V1 into V1 transpose will be, so let me do it here. So, V1 is 1 by root 2, 1 by root 2, 2 by 1, and V1 transpose is 1 by root 2, 1 by root 2. So, it will become 1 by 2, 1 by 2, 1 by 2, 1 by 2. So, it is n into 3. So, it will become 3 by 2, 3 by 2, 3 by 2, 3 by 2. This is first term plus now second term. So, V2 into V2 transpose and multiplied by eigenvalue 1. So, it will become 1 by 2 minus 1 by 2, this is again minus 1 by 2 and 1 by 2, means similarly you can calculate it. So, now you can see these two are nothing just projection matrix, okay, and it is the spectral decomposition of A. You can add these two, you will get the matrix A. It is also having rank 1, you can easily see both rows or both columns are same, they are LD, and here also both the columns are LD. So, rank 1. Okay. So, in this way we can calculate the spectral decomposition of A. So, with this example let me close this lecture. Thank you very much.